Hey everyone, so this is the next part that we have to cover when it comes to forces. So we just finished talking about Newton's three laws and friction, and for the most part, that stuff is not going away, and we're going to be seeing different ways that we can actually use those equations, different scenarios. So what the next few things that I have to talk about in this unit are some unique scenarios that we can apply Newton's three laws and friction into it. So this setup is called the multi-mass system. Now, the big thing to take away from this unit is that we have to make a distinction between systems and objects. So for the most part, we've been doing problems where we've simplified everything. If we had a person sitting in a car, we never really took into account everything that's going inside the car. We never talked about the engines going on. We never talked about the person sitting in the car. We just treated it as one solid object. So in this class, an object is actually defined as something that either doesn't have an internal structure. Uh, in real life, and not having an internal structure would be something like a particle, but more realistic, that could be something like a ball bearing, some sort of solid metal object. For the most part, there's really not an internal structure in there, it's just solid. Pretty much anything that is solid can be thought of like that. Or it's something that the internal structure doesn't matter. So if we have something that actually does have different parts inside of it, we don't actually care what's going on inside. Again, you sitting in your car, technically there is an internal structure for your car, but as far as we're concerned with some of the mathematics, it doesn't matter. We can just simplify it and just ignore it. So that's what an object is, and then a system is defined as a collection of objects that are interacting with each other. So far we've been doing problems where we've only really been looking at objects, but now we're going to take it a step back and look at objects as systems, and kind of see how we'd have to deal with a case where we have multiple objects interacting with each other. So here's a perfect example of what this means. Let's say in this scenario, I am applying a 45 Newton force onto a 5 kilogram block, and that 5 kilogram block is directly in contact with a 10 kilogram block. And I want to know what is the acceleration of the 5 kilogram block. So try this yourself. We'll go over it in a second. So this is a very common question. This pops up pretty much all throughout the different levels of physics. The most common thing that you would do is use F net equals ma. We have the 45 Newton force. They want to see the force on the 5 kilogram object. You might think that the 45 newtons is on the 5 kilograms, so that should be fine. We plug those numbers in, and we should get about 9 meters per second squared. Unfortunately, that is not correct. Instead, what we have to realize is that even though I'm only applying the 45 newtons onto the 5 kilogram object, and even though they do only ask about the 5 kilogram object, this is a system with two objects being interacting that are interacting with each other and being affected by the 45 newtons. Even though the 45 is only directly touching the 5 kilogram block, it is still being impeded by the 10 kilogram block. Because when I push the 5 kilogram forward, that 10 kilogram block is adding more resistance to that 5 kilograms motion. So I have to make sure that I include that as well. I can't treat it as as the 5 kilogram object being completely unique and unhindered by the 10 kilogram object. So there's a few ways I could go about this. The first way is I can actually treat this as one entire object. I could treat this like a system. By treating this like a system and looking at it as if it was one single object, I can realize that even though the 45 is technically only touching the 5 kilogram block, it's affecting both the 5 and the 10. So I can consider it as being affecting the 15 kilogram block. Uh, so I can make an FBD where for the most part I ignore the fact that this is technically two blocks and just treat it as one big block. So there's a force of gravity, a normal force, and applied force. I plug these numbers in and I'll get 3 meters per second squared as my acceleration. Now, if I don't want to do it this way, I can go a slightly more roundabout way and separate the blue and the yellow block. If I draw an FBD for the two individual blocks, I end up getting this. So the blue block is the only one that feels the applied force pushing it forward, the 45 newtons. So if I do an FBD, it would look like this. Now recall, one of the things I mentioned is that anytime an object is touching a surface, there's a normal force. So there's a normal force from the ground pushing it up, but the 10 kilogram block counts as a surface. So when the blue block pushes up against the 10 kilogram, that 10 kilogram is pushing it back. So there is a contact force between them. Now, technically this is a normal force, but we're going to want to call this a contact force just for our own sanity so that we don't have 100 normal forces going on, because there could be situations where we have, we already have two normal forces here. It'll get really annoying if we have, a third normal force. Not only that, it's going to be a hassle trying to keep track of which ones are equal to each other, especially if we add in a third one. So let's just keep it with F contact for that interactive forces. It also helps us in a second. So this is what our FBDs will end up looking like. Now, one thing I want to, I forgot to mention about the 10 kilogram block. This one does not have an applied force pushed onto it, only the contact force. We know that there's got to be a contact force forward because, first off, we know that it's going to end up accelerating forward because the blue block is pushing into it. So the blue block's pushing from this side, so there should be a force going in this direction. The applied force isn't on there because it's not physically touching it. And the one thing that we can tell off the bat is that since these are both contact forces caused by the interaction, because of Newton's third law, I know that for every action there is an equal and opposite reaction. So these two forces are actually the same. So whatever force I get here, that's the same that goes here. All right, so this is actually going to be a very strong and important thing to recall, is that these interactive forces, when we have systems that are moving together and affecting each other and moving as solid objects essentially, the contact forces are the same. Now, how do I go about doing this? Well, we basically do the same equation. We do F net equals ma. Now, I didn't actually type this up, which is a little unfortunate, so you're going to have to pay attention to my handwriting. In here, this object is accelerating to the right. So if I do F net equals ma, my net force is being caused by the applied force and the contact force. So it's going to end up being the 45 Newton applied force minus this contact force. And that's going to be affected by the 5 kilogram mass accelerating at some rate. For this one, it's a little bit simpler. I still use F net equals ma. This time there's only one force, the contact force. And for this one, the mass is going to be 10, and the acceleration is still a. Again, both these have the same acceleration. Now, I can't solve any of these equations by themselves, which is why we have to use two equations, two unknowns. Both these equations have two unknowns, an a and a contact force. So having these two unique equations, I can plug them into each other and simplify. So taking this first equation, 45, instead of writing F contact, I can put in 10A. And right off the bat, we can already see that we get the same setup that we got before. That we end up getting the net force of 45 is affecting the total 15 kilograms, and we once again get 3 meters per second squared. So apples to apples, we end up getting the same thing regardless of the setup. So a common question you might ask is, why would we even do this? Why not just treat it as one object? One reason is because it sometimes isn't easy to visualize what that might look like. You'll see why I say that in probably the next video. But another reason we're going to do this is because not only are we going to be asking about the acceleration, we're going to want to know about this contact force. If I treat this as one solid object, the contact forces cancel out, as they should. But if I treat them as separate objects, and I only use F net equals ma for one of them, then I could find out information about the contact force and the net force that's affecting these two objects. So this is going to be a very important thing to take away. So in conclusion, when you're doing a multi-mass setup, you're going to find the acceleration by treating this as a system of one object, essentially. You combine it all together. Uh, and if you're looking for either the interactive forces, the contact forces, whatever force is connecting them, or you're trying to find the net force, something that's pretty much unique to the object, you have to treat them separately. You have to treat them as separate objects. The one thing that you want to make sure that you do remember is that we're using F net equals ma this entire time. Like I said, we're still applying Newton's laws. We're just applying them into unique scenarios. So here's the first question. Pause the video, work itself. We'll go over in a second. All right, so the first part says, what is the magnitude and direction of the acceleration? So what I want to do, even though they specify a block B, they're moving together. Block B's acceleration is block A's acceleration, so they're the same thing. This force is affecting both, so realistically the question is asking, what's the acceleration of the system? So I'm going to treat this as one complete object of 3 kilograms. There's a weight going down, normal force going up, and just an applied force going to the right. So if I use F net equals ma, my net force is the 12 newtons, and the mass is the combined 3 kilograms, and I get 4 meters per second squared to the right. For part B, they want the magnitude and direction of the force exerted on block A by block B. So this is one of those interactive forces. This is the contact force that they want. So I have to look at this as two separate objects. Block B has an FBD that looks like this. Block A looks like this. For the most part, for these scenarios, they're pretty much all going to look very similar. We'll see what it looks like when there's a friction involved, but this is what the FBDs will look like. Now, I have my choice between which FBD I want to find. As I said before, the contact forces are equal and opposite. So even though they technically specify that they want block A's contact force, that's the same as the force on block B. So what I can do is I can do B and then it will be the same. So that's what I'm going to do. You're going to see me do this a lot where I choose the simpler of the FBDs just to make my life easier. Once again, I do F net equals ma. For block B, the only force is that contact force, and it's affecting the 2 kilogram mass. Plug in the acceleration, and end up getting 8 newtons to the left. Notice that the contact force on B is to the right, but I have to recall that I technically do want the force on A. So I have to switch it and remind myself that the contact force is to the left. You could have done this for block A. It would have been a little bit longer. What you would have had to do was the net force would have been 12 minus the contact force, and that would have been equal to 1 times 4, so it would have been equal to 4. Move some things around, and you would have gotten 12 minus 4 equals the contact force, and that just gets you back to the 8. This is actually a really good check for you to do. I highly recommend that anytime you're doing a multi-mass setup is to, even though you only have to do one of them, do both of them and then compare. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so this question wants you to solve it in terms of F. I know it wasn't really clear on that, so that my final answer should be some multiple of F. So here they want the force, again, they want that interactive force, that contact force. There's a few ways to go about it, but I'm going to go this, what I think is the simpler way. First thing I want to do is treat it like one complete object. Again, the FBD looks exactly the same. The whole point of this is for you to get practice treating it as systems and as objects and just getting used to the whole general setup. You'll see what a more complex multi-mass setup looks like. So we do F net equals ma. The only force applying is at F, and it's affecting the entire 6 kilograms. So my acceleration for the system is 1/6 of F. I did drop the kilograms just for convenience sake. Now we get to finding the contact force, so we treat them separately. Again, my FBDs are essentially the same thing as we had before. Only the F is only affecting the 2 kilogram block, and then the contact force is affecting both of them, equal and opposite. Again, I can choose whichever block I want to use F net equals MA again. I'm going to choose the 4 kilogram block just like last time. I plug in the F divided by 6. Again, recall that this technically has units of kilograms, so the 2 kilograms cross out. So I'm left with 4F over 6, and that's going to simplify to 2/3 F. So essentially the contact force that both of these blocks are going to be experiencing is 2/3 of F. All right. Here's the next question. Pause the video, work itself, and we'll go in a second. All right. So just a pretty standard multiple choice. You can actually solve this just by whatever ones conflict with what makes sense. For example, A doesn't make sense at all. There's no reason why the two blocks should accelerate differently. Even though they are unconnected, one's pushing into the other. So as long as this maintains its acceleration, this will match that acceleration. The only way they will accelerate differently is if this stops and decreases the acceleration while this one continues through, actually no, that would I would have to decrease the acceleration so much that it would actually go backwards, and then this could move at a constant speed. So that would be the only time where their accelerations would be different. But as long as one of them is accelerating, the other one should match it. Now, so that one's wrong. Block B doesn't make sense either because it violates Newton's third law. It says that the 3m mass exerts a greater force on the 4m than vice versa, but we know that Newton's third law states that they have to be equal. No matter the scenario, even if it seems implausible for it to make sense, Newton's third law has to hold. So that one's also wrong. So my answer is C, that the net force on the 4 kilogram block is greater than the net force on the 3m block. So the reasoning is as such. F net equals ma. Again, Newton's second law always holds. We know that for a fact that acceleration has to be the same. So that means that F net is proportional to m. If you've ever never seen this symbol represents proportional to. It's a math symbol. It's a way of saying that that as one increases, the other one increases by the same ratio. If I double mass, I double my force. If I triple the mass, I triple the force. Because those are the only other variables in this equation that can change, essentially. So just pointing that out. You don't ever have to use it, but you'll see me using it a lot. So because F net and m are proportional, that means that an increase in mass implies, again, another math symbol, that the F net also has to be bigger. So the bigger mass requires a bigger net force. This is actually one that a lot of people tend to forget. Again, a lot of people tend to think of Newton's third law and think, oh, the net forces have to be the same because they're interacting. But again, that just mentions the contact force. The net forces will end up being different because their accelerations have to be the same. This is slightly different than the cases where you have a cannon firing off a cannonball and they kind of get shot off in different directions. In that case, the net force actually is the same because of Newton's third law. But the difference there is those two objects were free to change their have different accelerations. They were allowed to accelerate differently. And not only that, the contact force on both of them was the only one that was actually providing the net force. Here, we have an outside force affecting the system, so that kind of changes things up. But we also have a setup where the accelerations have to be the same. All right. So let's continue this and actually do the calculations. So pause the video, work itself, and we'll go in a second. All right, once again, they want that contact force. So I'm going to do the same thing I did in the last problem. I treat it like one object, plug and chug, and I end up getting the applied force divided by 7m. Now I want that contact force, so I'm going to do another FBD of them separately. I'm going to look at the 3m block because of the fact that it only has the contact force. Do F net equals ma, plug my acceleration that I got from before. Once again, the masses drop out. So I end up getting that the contact force is going to be 3/7 of the applied force. And that's it. That's pretty much the basic setup for multi-mass systems. We'll see in the next video more of the special, unique, very common. I don't want to say complex, but more complicated setups that you can do with the multi-mass systems. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.